Hello, Professor, and hello, everyone. Uh, we are a team of three consisting myself, Harshavardhan, and Pooja, and we have worked on the project Simple GAN for Pattern Recognition for the course ECE 5831. And coming to objectives, in this presentation, we are going to discuss about the following. Introduction, where we'll discuss about the role of GANs in pattern recognition and data generation, and also about the MNIST dataset which we have used in this project, and the extension to generating the fake data for the California house pricing, and abstract, where we'll talk about the project objectives and the significance. Background, where we'll talk about the GANs and their importance, and also the problems of the limited datasets in pattern recognition and data generation. And next one is MNIST dataset. Here we'll discuss about the MNIST dataset and also the significance in the context of the image recognition. And coming to simple GAN architecture, here we'll discuss about the overview of the simple GAN architecture and also the explanation of the generator and the discriminator components. Training process. Here we'll have the explanation of the training procedure for the simple GAN. GAN. Coming to the results of MNIST, we will show the sample results of the pattern recognition on the MNIST dataset. Extension to California house price prediction, where we'll introduce the extension of GANs for generating the synthetic data, and experimental results for house price prediction, where we'll display the sample results that we have got of generating the synthetic data for the California price prediction, and at last conclusion. Coming to the slide, introduction. Our project is mainly focuses on the innovative application, which is a creative tool called GAN, which helps computers for making more realistic data. First, we use GANs to recognize patterns in handwritten digits using the MNIST dataset, making computer programs understand and also generate the same lifelike numbers. Then we take it a step further by using the GANs to create the fake data for predicting the house prices in the California, which helps us solve problems that when we don't have the enough real data. This shows how GANs can be super useful in making the computer smarter and also overcoming the challenges with not having the enough information, like limited datasets. We can see here. Coming to abstract, our project explores the transformative applications of the GANs in both the regions where pattern recognition and also the generation of the synthetic data. Initially, we employ a simple GAN to recognize the patterns within the dataset, the MNIST dataset, showcasing that its effectiveness in the image recognition. The simple GAN acts as a creative assistant, which learns from the existing handwritten digits from the MNIST dataset, which we have explained, which we have discussed, and generating the realistic new ones. Building on our success with the pattern recognition, we extended the capabilities to the GAN to generate the synthetic data for predicting the California house prices. This innovative application addresses challenges which are related to the limited real world data, providing a solution for more robust and like predictive modeling. The extension to the California house price prediction explains the GAN's role in overcoming the data scarcity challenge, making it possible to generate a meaningful data even when the the real data sets are limited. In the diagram that is attached in the slide number 4, these networks are trained simultaneously, engaging in adversarial process where the generator gets better at creating realistic data and the discriminator becomes more adept at telling what is real and what is fake. GANs generate the synthetic data that closely mirrors the distribution found in real data, effectively expanding and training the data sets, expanding and diversifying training data sets by overcoming the data set limitations. GANs enhance model adaptability and generalization, leading to more robust and accurate AI models. And the next slide will be continued by Pooja.
Classification techniques. The MNIST is relatively clean, but some common processing steps may include normalization to scale pixel values between 0 and 1 and flattering the 28 into 28 images into a vector format might be considered. Going to our GAN architecture, our architecture of simple GAN comprises two key components, which is generator and discriminator. The generator takes random noise as input and transforms it into synthetic data, whereas the discriminator evaluates input data, discerning between real and generated samples. It also learns to accurately classify the data and provides feedback to the generator for improvement. In the training process of a simple GAN involves an adversarial interplay between the generator and discriminator. There are four key parameters in the training process, which is learning rate, batch size, epochs, and noise dimensions. Here the learning rate is 3E4, batch size is 32, epochs is 100, and the noise dimensions is 64. The discriminator and generator are initialized. California housing data is loaded and processed using standard scaling. Here are the discriminator visualizations and generator visualizations. For our sample GAN, we have done both discriminator visualization and generator visualizations. You can see the difference of both visualization, that the last layer of the discriminator visualizations is sigmoid backward, and for the generator it is tanh backward. The model architecture of discriminator is two fully connected layers with leaky ReLU activation and sigmoid activation for binary classification, whereas for generator is two fully connected layers with leaky ReLU activation. ADAM optimizers are configured for both discriminator and generators. Binary cross entropy loss is chosen as the loss function. For each epoch, iterate through batches of real data from the data loader. To train the discriminator, generate random noise and create fake data using generator, and evaluate real and fake data with the discriminator and calculates BCE loss. To train the generator, generate fake data using the generator and evaluate the discriminator's output for the generated data and calculate BCE loss. Thank you.
So let's dive into our results on our project. So let me quickly show you a live demo of our project. So what we did is like we created a simple GAN architecture, and then we given the MNIST dataset to it, so that we can generate the fake. It can generate the fake MNIST dataset, and then after successfully generating the fake dataset of the MNIST, and then we extended our project to the California housing data. So while coming to the MNIST GAN, so here we have done everything on the Google Colab. So first we have imported the dependencies. We have used the PyTorch depending framework here, and then we wrote code for the discriminator module and then for the generator module. And here we have include the hyperparameters and the number of epochs 200, batch size 32, and all this we have discussed earlier. And we have loaded the tensor board for the visualizations of the how we can see how the numbers are changing so that we can see the progress. So while coming to the code part, here first we imported the dataset. First we have loaded the dataset. Here our GANs architecture starts with the loading MNIST dataset. We have our datasets.mnist, as we can see, to download and process the images, and then while coming to the data loader and optimizers. Next we have a data loader, which is crucial for the managing data in manageable batches, and we have here used the Adam optimizer for both the discriminator and the generator. And while coming to the training loop, we have handled both the real and generated images. The discriminator learns from the real images, and the generator creates fake images using the noise vector, which is for batch IDX. While coming to the loss calculation, the loss for both the discriminator and the generator is calculated using the neural network.bce loss, which is nothing but the binary cross entropy loss. Is a standard in training GANs for binary classification tasks. So TensorBoard logging. Welcome to the TensorBoard logging. We have used the TensorBoard for logging, and we have used fake.add image and the real.add image methods are used to log the fake and real images respectively for visualizations. So here now I'm going to quickly show you how the images are getting trained from the first step onwards. As you guys can see, how the MNIST dataset, how the generator is able to quickly learn the images and fool the discriminator. We can see how the noise is being reducing and the images are being sharpened over the steps. So after generating the successfully 200 epochs, we got to see the loss of the discriminator and the generator has been optimized to the medium levels. So now we have done with the MNIST GAN. So now we will export the same GAN architecture to the columnar dataset, which is nothing but the California housing dataset. Let's see how these GANs can work on that. It's the same. We have done everything, including the coding part. We have imported the necessary dependencies using the PyTorch library, and we have defined the discriminator and generator in the same way for the MNIST and for the hyperparameters, except we have trained it for the less period because we have taken the less data, and all the data sets are from the PyTorch only. While coming to the loss, here also we have taken the binary cross entropy loss, and it is also for the columnar dataset. It can also be, these type of losses can also be used for the columnar datasets. As while coming to the slides, you can see how the dataset is distribution in the generator. It's completely random noise, and we can see down the blue on these real ones. And the generator aim is to match the distribution of the data to the real images, so that it can fool the discriminator. As we can see how it's changing random noise distribution to the peaks. At the last step, we can see how it's actually sharpened and it's almost trying to match the distributions of the real ones so that it can further discriminate very well. And on the right hand side, we can see it's a distributions of the it's a distribution of the data sets in another format. We can see how it's flat for the real housing data and it's on the first cycle of the generator, and the aim is to match those distributions need to be flat. So while at the last cycle we able to achieve the flat ones. So we're coming to the conclusion. So this project establishes the GANs as a valuable asset in generating synthetic data for predictive modeling, with broader implications for addressing data scarcity challenges across various domains. So that the companies need not to pay too much of the money on gathering data. Just using the best models of the GANs, we can generate the synthetic data and then we can use it for real-time analysis. So the successful extension of GANs to the real estate domain underlines the adaptability and potential impact in diverse applications too. And the successful implementation and training of a simple GAN for generating synthetic data in the context of California house prices were successful. And thank you.